In this video, we will be deriving the differential equations of electrical circuits. We're going to solve three problems. We'll start from the easiest and end up with the hardest one. So the first circuit we're going to solve is this one. And we are to derive its differential equation or equations. So the first thing is to find out how many memory elements there are in the circuit, because the number of memory elements will determine the number of differential equations that we end up with. So a memory element, just a tip for that, all the reactive elements in the circuit are memory elements. So if we look at carefully, we'll see that the inductor and the capacitor, they are reactive elements. So therefore, there are two memory elements in the circuit. That's the first tip. Then the second thing is the final results of the differential equations. The deal is that there are certain variables that are allowed to be in the final result, and there are some that are not allowed. So the entire essence of solving this question or deriving the final equation is to substitute or eliminate those variables that we don't need. So the variables that are allowed or permitted to be in the differential equations are as follows. I'll write them here. The state variables, and the state variables, there are two. Voltage of the capacitor is one of them. Current of the inductor is another one. And so those are the two state variables. So you don't confuse them, it is the voltage of the capacitor. The current of the capacitor is not a state variable. The voltage of the inductor is not a state variable. But the voltage of the capacitor is a state variable, and the current of the inductor is a state variable. So these are the two state variables, and they can't be in the final differential equation. Then there are parameters: resistance, inductance, and capacitance. These are constants, and they can also be in the final form of the differential equation. So for example, you see R1, oh, I forgot to label this one, R2. They can be in the final result. Then also, you can see the input signal. Now, take note of that. If it's a voltage source like this one, then the voltage of a voltage source is allowed, not the current of a voltage source. The voltage of a voltage source is allowed. Then also, assuming it was the input signal was a current source, let's assume IB, for example, then the current of the current source is allowed. So I'll just write it here. Voltage of a voltage source and the current of a current source. So it therefore means that the voltage, the current of a voltage source is not allowed, and the voltage of a current source is not allowed. So just for the notice, just to take note of it, what are not allowed? The following are not allowed. The current of a capacitor is not allowed. The voltage of an inductor is not allowed. And then the current of a voltage source is not allowed. And the voltage of a current source is not allowed. So the essence of solving this is to end up with all of these variables. Like any one of them that you end up with is okay. If you have these ones in your variables, you have to remove them. Now, I said that this and this is not allowed, but so just don't worry, I'll make a point later on as we continue. Now, I haven't realized the destination, the final results that we want, like what we need, and then realizing that we have two memory elements. So we can take any one of them we like, start from anyone. So I will just start with inductor. For the inductor, we know that the voltage across an inductor is equal to the inductance multiplied by the time derivative of the current of the inductor. Good. So the point I was trying to make is, yes, indeed, this is not allowed to be in a final equation. You have to eliminate it. And the way you do it is to substitute the right hand side for whatever you have at the left hand side. So now you have this equation, this differential equation. What do? You try to formulate structural equations from this circuit that you can use to substitute the left hand side. Let me quickly do that. So now this is the inductor. You look at the neighboring region around the inductor, because inductor has two terminals. Just look for anything around it. First and foremost, because you have a voltage here, then a merge current analysis, a merge current approach will be better, like using a loop method. KVL will be easier to make use of. So you can see, what merge does the inductor belong to? It belongs to the first merge. This is the first merge, this is the second merge. So therefore, you make use of this merge to form a structural equation. So before we do that, this is direction of current. I've made an assumption that this is direction of current for this branch, and then this is the direction of current for this branch, and then this is the direction of current for this branch. Another thing that I do to make my life easy is how I name the currents. Now, I like to start with the memory elements. So because inductor is along this branch, I'll call it IL. Okay, let me rename it here. I'll call it IL. That's the current of inductor. That makes my life very easy, because I know that it will be part of it. Then because the capacitor is along this branch, I will call this current the current of the capacitor. So it means that by doing it this way, I'm reducing the number of equations I'm going to write. So that makes it, yeah. Then for this one, there's no memory element on this branch. So I go ahead and name this current the current of the resistor R2. Yeah. So this method makes it easier for me, reduces the number of equations and substitutions that I need to make. Now, I haven't done this one. As I said, because there is a voltage on this side, on the left-hand side, I'm going to use KVL to go about it, or the merge current analysis. So if that be the case, I will make use of this loop, because the inductor in question is on this loop, and I'll call it the first loop. So loop 1 or mesh 1. Now, if that be the case, I start from here, going along in the direction of the current, going along the direction of the current. This is the voltage source, right? So if I'm going along the direction of the current from the negative side to the positive side, from less voltage to higher voltage of the voltage source, because the voltage source is supplying energy, then it's going to be a positive, and in fact there's an increase in voltage from year to year, so across the voltage source, so it's going to be UB. Now, going through in the direction of the current, going through the resistor, there's a drop in voltage, and that drop in voltage is the drop in voltage across the resistor R1. The same thing with L. There's also going to be a drop in voltage, and that will become minus UL. And then going down here back to ground, again minus UR2 equals to 0. I forgot to add to the list of not allowed. What are not allowed? Other forms of voltages of the elements, like voltage drop of various elements, like that of UR, for example, all of them, like UR1 and UR2, is not allowed. So we have to find a way to eliminate these ones. And if you look carefully, you'll find out that we can use Ohm's law, because they are resistors, right? We can use Ohm's law to do substitution or elimination. So rewriting it, we have UB in parentheses resistor 1 multiplied multiplied by the current of the inductor minus UL. And you don't need to do anything with this yet. You can substitute this one here, but I don't like to be in a hurry because sometimes the mathematics is more involved. Like the third question, we'll sit in the third question. So that's why I preserve it for now. It's usually the last thing I do, substituting this right-hand side for it. Then minus. Now, another tip, a very important tip I want to give here is this. Whenever you see a resistor in parallel with a capacitor, it really makes your life very easy because the voltage across a capacitor will be equal to the voltage across the resistor. And that is, the capacitor has to be on its own. No resistor is in series with it. Just a resistor being in parallel with it. It's a beautiful thing. Very, very beautiful stuff. It makes your life very easy because the voltage across the capacitor is what we can also include in the final equation. So you don't need to solve again for this one. See, UR2 is also equal to UC. Therefore, you put UC there equal to 0. See how simple it is. Now, what do we have here? Let us look at our equation at this stage. This is allowed. That's the voltage of the input voltage is allowed, or the input signal. R1 is allowed. The current of the inductor is allowed. This one, we will substitute this into it finally, but let's leave it first. And indeed, the voltage of the capacitor is allowed. The equation is complete. You don't need to solve any further. That's the beauty of it. What we just need to do is to make UL, that is this one here, make it the subject of the formula. And that becomes voltage across the inductor is equal to the input voltage minus R1 multiplied by IL minus voltage across the capacitor, right? 1, 2, 3, yes, that's it. Then when you've got to this point, you can now substitute this one because there's nothing more to do. And that becomes L dot DIL subscript L dt, right, is equal to UB minus the voltage across the capacitor. This is the first differential equation we are looking for, right? So the second one is for the capacitor. Now we can write it out here. The current across a capacitor is equal to the capacitance multiplied by the time derivative of the voltage across it divided by, time derivative, you know what I mean? All right, now, again, we look at this equation. We need the right-hand side in the final equation, but we don't need the left-hand side in the final equation. So what do? We try to derive or formulate a structural equation that would eventually eliminate the left-hand side, I subscript C, that's the current of the capacitor. So we go back to our equation. You see, this is where the capacitor is located. In the neighboring region of this capacitor, look for, and because we have current, the node voltage analysis or KCL will be very relevant here. We make our life easy. So now, the capacitor has two terminals, right? Either to this side or to this side. Look for the junction, the nearest node that you want to make use of. For me, I will use this one here at the upper side. And so at that node, let's just call it node A, right? At this node, at node A, any incoming current is positive for me, and the outgoing current is negative. At node A, the current of the inductor, which is this one, it goes all around to this side, minus the current of the capacitor, IC, because the current of the capacitor is leaving, and the current of resistor 2 is also leaving too, minus I R2 is equal to 0. Nice. So when we have this, it means that we can substitute this differential equation into the current the current of the capacitor, but not so fast. I like to do this last. I like to do it last because we don't know how complicated trying to eliminate others or substitute for others might be. So we hold on first. The next thing is we look at if there are variables that are not allowed in the final form of the differential equation. And of course, we can see that the current of the resistor is not allowed. And so let me even add to the list of not allowed here. All currents of the resistors are not allowed. The current of all resistors are not allowed. And so if that be the case, what do? We have to substitute for it. And so we go back and we check for I2. So because we have current, the first thing we do is to use an element equation because, you have current of resistor 2. You can convert that. You can convert it with the relationship of resistor 2. So for resistor 2, we know that, let's just focus on resistor 2. We know that the voltage across resistor 2 divided by resistor 2 is equal to the current. Now, having done this, you now have this is allowed and this is not allowed. But you can see that even if the voltage across resistor 2 is not allowed, you can see that resistor 2's voltage is equal to the voltage of the capacitor. Therefore, you can also say that I2 is equal to UC divided by RO2. Now, RO2 is allowed, UC is allowed. So we cannot substitute it here. So therefore, the current of the inductor minus the current of the capacitor minus the voltage of the capacitor divided by RO2 is equal to 0. We're almost there, almost. Now, IC is not allowed in this form, but we can always substitute the differential equation on the right-hand side here for it. So therefore, before we do that, let us make IC the subject of the formula. So IC is equal to the inductor current minus the voltage across the capacitor divided by RO2. We cannot substitute the right-hand side of the differential equation for the capacitor. And that becomes C dot du C divided by dt is equal to IL minus UC over RO2. This is our final differential equation. Equation 1 and equation 2 are the final differential equations that we need. And the reason why it was this simple is because of the design of the circuit or the configuration of the circuit. Anytime you see a resistor in parallel with a capacitor, you know your life is going to be easy. And if you see a resistor in series with an inductor, you also know your life is going to be easy. This kind of configuration makes it easy because we know that the current of the inductor is one of the final results that we need. And this resistor 1, has that value. That's why it streamlines the process. And the same thing with voltage. The voltage of the capacitor is in the final form. And so RO2 shares the same voltage with the capacitor. That's why some steps are eliminated. So the design of this circuit or this circuit configuration makes your life easy. So we'll go to the second question next.